Okay, we're almost done. Second to last lecture. Malware. Again, we're mostly into the kind of special side topics at this point, so things are going to get a bit more conceptual, which is good. And so you can just sit back and kind of enjoy the brief overview of this very complicated topic. Before we do that, let's just have some announcements. Let's see. There's a homework. This is the last one. It's due next Monday. There's a project. It's due next Tuesday, so we have about a week. Again, this project is shorter than the first two, so hopefully a week is enough. There's a project. It was supposed to be due Tuesday, but we've extended it to Friday because it seemed like people were feeling stressed out about it. So hopefully that gives you a bit of extra time to finish your design. This does mean projects 2 and 3 kind of overlap, but again, hopefully project 3 is short enough that this will work out. There's a final exam. It's next Thursday. There's a conflict form if you can't make this time. There are 2 optional labs. They're both out now. They're due at the end of the semester. So if you have time, feel free to give them a look. SID's discussion is still canceled because no one was showing up. So we'll just make them office hours for now. And next week, just like for the midterm, we'll be doing optional review sessions. The worksheet should be up soon-ish, I hope. And the last lecture is tomorrow. That's in scope. So the final will test all the way up to tomorrow's lecture, which is tour. And then next week is all just good stuff, fun, random lectures. So Nicholas is doing one, I'm doing one. We might have one of the TAs do one, but it should all be just kind of fun side topics, applications, but none of it will be in scope. So they're all optional. If you want to stay home and study, that's totally fine. Or if you want to come and see some random fun applications of security, you can do that too. Okay. So let me try and slow down with the summary since we had to speed through it last time. First, yesterday we talked about path traversal attacks. And a path traversal attack is when you authorize an unauthorized file by exploiting Unix file path semantics. So remember, in a Unix file path, there are a couple special characters. There's the slash for directories or folders. There's the single dot for the current directory. And then there's this weird one, the 2 dots dot dot, which refers to the parent directory. So if the user is allowed to input any file path, and the user inputs something like dot dot slash dot dot slash dot dot, the user could actually jump into other folders that they're not supposed to be accessing. And that lets the user maybe access something secret, like a passwords file or something that they're not supposed to access. So the problem here is just like the problem that we saw in, say, SQL injection or XSS, which is that user input is being treated as a file path. So we're interpreting the user's input as code or file path when it shouldn't be. And the defense here is just to make sure that we're not treating the user's dot dot slash as a command to go into the parent directory and go into other folders. Instead, you should just use the user's input as a file name or something. Okay. So then we talked about a couple types of detectors. So we're going to use path traversal as an example to motivate the rest of last time's lecture, I guess. And so we talked about intrusion detection. So if we can't prevent attacks, then we should be able to at least detect them. And that was all of last time. So we talked about there's something called a NIDS, or network intrusion detection system. These are installed on the network. So a single NIDS is enough to cover an entire local network because every single packet from the network going to the internet will pass through the NIDS, and every packet from the outside internet into the network will pass through the NIDS. So the NIDS will monitor everything, and the benefits here are it's a single device for the whole network. So that makes it cheap, it's easy to scale, there's simple management because you just manage a single machine. It doesn't have to touch any of the end systems in the network, and you have a small TCP that you have to trust. So that's good. The problems here are the NIDS is only looking at network packets. So if you look at network packets, those actually could be different than what the end host sees. So for example, if you have a TTL that has not expired at the NIDS but will expire before it hits the end host, then the NIDS is going to see a packet that the end host doesn't see. Or if the NIDS interprets a packet one way, but the end host interprets the packet another way, then you have this inconsistent interpretation. And attackers can leverage this using something called evasion attacks. So they make a packet that looks good to the NIDS, so the detection system doesn't detect it, but the end host does still get attacked. So it's an attack that looks okay to avoid detection, but is still an attack. And then we said NIDS also have the problem that if traffic is encrypted, the NIDS is unable to read the traffic over the network. And you can solve this by doing something kind of weird, like giving the private key to the NIDS so they can decrypt it, or letting the NIDs be a full man in the middle or something like that. But those are all kind of gross or kind of weird solutions, but you can still do that. And the alternative here is to use a HIDS or host-based intrusion detection system. So instead of installing on the network, this time we install on all of the end host machines. So this solves all of those inconsistent problems from before because the end host, which is interpreting the packets, is also where the detector is. Sorry. The end host, which is interpreting the packets, is also where the detection system is installed. So they're both looking at the same perspective on these packets. That also helps with encrypted traffic because if our encryption is end-to-end secure, then the detection system is at one of the ends, so they'll be able to decrypt and look at the decrypted traffic. And then this is good also because it works inside the network, so the NIDs will help us defend attacks from outside as they come inside, but the HIDS also helps us prevent against attacks within the network. So if one of the employees is trying to be malicious or something. And then the performance can scale okay in that if you're worried about denial of service attacks, well, the NIDS is a single machine, so you can overwhelm that, but the HIDS is several machines, so it's harder to overwhelm any one HIDS. And then the drawbacks are kind of the opposite of the NIDS. So because you have to install one machine per host, it's more expensive. And even though we solved a lot of evasion attacks by using consistent interpretation, there are still a couple that can still happen. So it's not perfect. And then the third option is a little bit different, but it's saying instead of actively detecting things as they arrive, now you rely on the server or the computer to generate logs of what's happened. And then you run a script on those logs to see if those logs have evidence of any attacks. This is really good because it's cheap. So a lot of servers already generate logs automatically. So all you have to do is take the logs, which are like giant text files, and then just run a Python script or something over the text file, and then you've done logging. That also helps with inconsistencies because logging is looking at the scripts or the logs generated from the server, and the server is obviously interpreting things from the server's perspective. So you don't have the problem with NIDS where you have kind of two different interpretations. The biggest problem with logging is that you don't find out about attacks until after they've happened, right? Because if something has been logged, it's already happened. So by the time you look at it, it can have already happened. If you look at the logs at night, it could have already been hours or days since it happened. So that could be bad. And again, evasion attacks can still happen. And an attacker who's sneaky could also just delete the evidence from the logs, in which case you'll never find evidence. Okay. Then we talked about how do you measure if a detector is good. So to do so, we look at how can detectors go wrong. And the two ways a detector can go wrong is if there's no attack, but the detector incorrectly says there is an attack, then it got it wrong. So that's a false positive. If a detector does not alert, but there was an attack that the detector failed to alert, and that's another mistake, so that's a false negative. And the accuracy is based on the rates of these. So a high false positive rate means that your detector is messing up a lot by always detecting or detecting very often when there are no attacks. And a false negative rate is bad if it's high because that says that even though there are attacks, the detector is constantly failing to alert on them. So you want to make these two rates as low as possible. And then we said it's possible to make a perfect detector. You could just say return true or return false, but those aren't really good or useful detectors. So if you want a good detector, you usually have to consider trade-offs. So some detectors are good in some environments, but terrible in other environments. So you have to look at your environment and think about what detector is best for your environment. And this depends on things like how often is your system attacked, or how much does it cost to solve a false positive, or how much does it cost to solve a false negative. So if you think back to fire alarms, that's a case where a false positive is not so bad, but a false negative is really, really bad. So I probably want a detector with a high false positive rate if I can get a very low false negative rate. Then we said accurate detection is very challenging if the base rate of attacks is low. So if you look at a statistical phenomenon called the base rate fallacy, we're not going to ask you to remember the specifics, but that's a fallacy that shows you that if the base rate of attacks is low, then when your detector picks up a whole bunch of alerts, chances are most of those alerts are actually false positives, and the true positives are actually kind of hidden inside that pile of false positives. So it's very hard to find the real attacks if you only have, say, 5 attacks out of 10 million. That's very hard. And then we said you can combine detectors. So maybe you have multiple detectors and you want to chain them together. You can chain it in parallel to say if either detector alerts, then I'll alert. Or you can chain in series to say if both detectors alert, then we'll alert. If only one of the detectors alerts, then I won't alert. And again, here's a trade-off. So if you use parallel, you reduce false negatives but increase false positives usually. And then in series, if you chain them in series, you have fewer false positives but more false negatives. So again, you have to look at the trade-offs and figure out, does this work for my application? Okay. So then we talked about how do you detect. So we talked about where to put the detector and how does it go wrong. But then we talked about how do you actually look at a packet or look at a message and figure out, is this an attack or not? And there are 4 main strategies you can use here. So you can use signature-based, which says have a list of all the known attacks. So these are all the patterns that I've seen show up in attacks. If any activity matches the patterns that I have listed here, then I'll flag. So that's blacklisting because it has a list of non-allowed things and you flag when something shows up in the list. This is really good for known attacks because you have this gigantic library of attacks that security researchers have put together. So you can just go online or ask a friend, download this huge list of millions of attacks, and then check every packet against all these known attacks. So that's good for known attacks. But if there's an unknown attack or a variation of an attack, then signature-based detection is poor and it won't be able to catch it. So if the attacker is able to modify their attack to avoid your signature, so they kind of change the pattern a little bit so that it doesn't match the signature, then your detection could fail. And then we talked about specification-based. So here you list what's allowed. So you say, if I'm running a C program, the user can enter numbers because I'm looking for their age. So I specify what's allowed, and then everything else that's not allowed gets flagged. So this is whitelisting because I list what's allowed and everything else is flagged. So if it's on the list, it's okay. If it's off the list, then it's not okay. So this is good for detecting unknown attacks because even if an attack isn't known, it's not going to be in the specification, so it'll still be flagged. But this can be tricky because you have to manually write exactly what is and isn't allowed. So if you have a whole bunch of different pieces of code, you have to specify manually what every code takes as input, and that could be hard. Then we have anomaly-based. So this says, I don't want to have to write those specifications. So can I be smart and fancy and use like machine learning or some model to determine what is and isn't allowed? So anomaly-based says you use some sort of fancy algorithm or machine learning to figure out what is normal activity. What does a normal request look like? And then using this model, you alert on anything that deviates from normal activity. So this is really high tech and fancy and uses all these fancy machine learning buzzword modern things. But in practice, it's not that good because you could use a poor model for prediction. So maybe your model was trained on bad data or your model is just not very good, in which case it could flag lots of false positives or lots of false negatives through. So anomaly-based detection usually is only great if you're doing research and writing a paper about it. But as of today, not a lot of people use this in practice. And then finally, we talked about behavioral detection. And this is saying instead of looking at the input and analyzing the input, you're actually going to analyze the result of the input. So I don't care how the input comes in. All I care about is what did the input do? Did it call a function? Did it open a file? Did it make this network request? So I look at what the input did. And that will show me if my system has been compromised. So if I see that the passwords file has been accessed, that could be a sign that something has gone wrong. And again, in behavioral, you can also use blacklists or whitelists. It's up to you. But this is kind of a general pattern of detection. And this is good because it's sometimes cheap. So a lot of logging systems already do behavioral for you. So like a server will tell you when a system function is called or when a packet is sent. So a lot of built-in tools already do behavioral detection for you. So that's cheap. And it can also detect new attacks because even if an attack is brand new, the result could still be something that I'm aware of, like passwords file has been accessed. But the problem here is that oftentimes you only detect after the attack has happened, right? By the time you notice that the passwords file has been sent over the network, it might be too late because someone has already stolen all your passwords. Okay, so those are the 4 methods. And then at the end, we give you a really, really quick overview of the other strategies that could be used. So there's vulnerability scanning, which says attack your own system. So with your own consent, find a tool that attacks your own system with a lot of common attacks. And if any of them work, then go back and fix those attacks. This is really good because you're preventing attacks before they even happen because you're trying them yourself. But it can be expensive. So for example, if you're not sure that an attack exists and you try out the attack and it ends up destroying your system, it can be very expensive to clean that up. But it could still be useful because it's better to destroy your system now and clean it than to have an attacker do it later. So it depends. Then there's the honeypot, and the honeypot is kind of fun. It says, in my system, I'm going to put a dummy sacrificial system inside. This system is not used by any legitimate user, which means if someone is accessing it, either they've messed up or they're an attacker. So this is really good because now not only do I figure out that an attacker is in my system because they've accessed the honeypot, I can also see what they're trying to do with the honeypot. So are they trying to find a passwords file? Are they trying to execute shellcode? What is the shellcode they're executing? So I can actually analyze the attacker while they're working on this sacrificial system with no risk. But this can be a little bit hard if I have to trick the attacker into using the honeypot. So maybe it costs some money or some effort to build a very convincing honeypot that the attacker will be attracted to. So if the honeypot looks fake, the attacker is probably not going to go to it. So that could take some work. And some examples of honeypots are like the stack canary, which we saw yesterday, right? That's a sacrificial system, which means if someone has accessed it, that would be a sign that something has gone wrong. Or you can put some Bitcoin money that's unsecured in the system, and presumably when an attacker breaks in, the first thing they're going to go to is the money, so that also attract the attacker to the honeypot. Someone asked if honeypots are security through obscurity. Yeah, I think it kind of is, because you're assuming the attacker doesn't know that it's a honeypot. Yeah, I think that might be a matter of like maybe opinion or how you build the honeypot. I don't know, maybe Nicholas has a better answer, but okay. Yeah, I think Nicholas says it's more defense in depth, which I agree with. So it's kind of like an extra defense that you can put on your system. So maybe defense in depth. But yeah, I guess it could be security through obscurity if you're assuming that the attacker knows where your honeypot is. So yeah, I guess it could be. That's a good question though. Then we talked about forensics. So this is saying if an attack has succeeded, then you probably want to do some detective work. Sorry, you want to do some detective work to figure out what went wrong. How come the attacker was able to come in? What attack did they do? What damage has been done? So forensics is kind of the art of analyzing what happened afterwards. And that is an entire field in of itself. So you can go into that if you're interested, but we just gave you a quick overview. And then we said some intrusion detection systems have a bonus feature, which is that they can also block attacks in addition to detecting them. And that's called an intrusion prevention system. So these are really good. And a lot of people use them today, although there is kind of the additional feature that you need, which is a detection system only has to read packets that come in and figure out if they're malicious or not. So all they have to do is have reading capabilities. But prevention systems might also have to have writing abilities, like they have to block packets or drop packets or do man-in-the-middle attacks to stop attacks. So you have to give the intrusion prevention system more power to do its work. And that could also mean something like a false positive is more costly because now a legitimate user got stopped by the system. But it is a good tool to use in modern days. So a lot of people do use those. Okay, so that was last time's very long lecture. Today I hope is a little bit shorter and it's still very conceptual, but today is all about malware, which is a large category of code that does bad things. So we're going to see kind of what are the categories of different kinds of code that does bad things, and also how do they spread. And there are a lot of kind of real world stories today of examples of viruses and worms that have done gigantic damage across the world. So that's kind of fun. Well, it depends on your definition of fun. And then at the very end, we'll really quickly tell you how to clean up malware. So let's first talk about what is malware. And malware is actually a kind of combination of two words. I forget what these are called. They're called portmanteaus, something like that. But malware stands for malicious software. So they took the mal from the first part and the ware from the second part, and they got malware. And this is just a catch-all term for any sort of attacker code running on victim computers. So lots of different things can be malware. You know, the shellcode from buffer overflows, that's malware. Or the payload in JavaScript or XSS, that's malware. So there are lots of different malware examples. Sometimes you see malcode. So instead of malicious software, they say malicious code, and then you combine those and you get malcode. But it's about the same thing. And again, this can kind of refer to any sort of attacker code. And what the code does isn't too relevant. It's all categorized as malware. So what are some things that attackers might want to do with malware? Well, this is kind of something we've talked about all semester, and that includes things like I want to delete files as an attacker, or send spam email, or do a DOS attack, so denial of service, or steal private information. So maybe leak someone's secret session token as your cookie, or find their passwords file or something. You can also do more evil things like recording user inputs. So keep track of what the user is typing, capture their screen, look at their webcam, so have a view of like what they're doing at home. Those are all things that malware could also do. You could also do ransomware. So in ransomware, you encrypt a file or encrypt the entire file system, and you say, pay me 10 Bitcoin or else I'm going to delete all your files. And if you pay me Bitcoin, then I'll give you the key to decrypt. And sometimes when you pay the Bitcoin, they'll give you the key. Sometimes they'll be like, haha, psych, and they'll decrypt. And if you remember from Bitcoin, Bitcoin can't be reversed. So if you pay the ransom and they delete your files, that's too bad. Your money doesn't come back. You can also physically damage machines with malware, and we'll see that today as well. So you can change some preferences to make the system hardware actually stop working. So yeah, there's a lot of different things you can do with malware. We'll see more examples today, but anything that an attacker would want to do, it can probably be classified as malware. And today's kind of main topic is how do we make this malware propagate? How do people try to detect malware, and how do attackers get around that? Okay. And just so we know, the word propagate just means spreading from machine to machine. So when a virus or malware propagates, it spreads across different machines. Okay, and how do we do that automatically is a big question. Okay, so to automatically spread malware, the main theme is something called self-replicating code. This is a very kind of funny subcategory of coding, and not a lot of people do it. It's mostly just people doing it for fun or attackers. And self-replicating code is basically a code snippet that outputs a copy of itself. So this code, it runs and does some action, but additionally, it also outputs a copy of itself to send to other people. So as you can imagine, this is used for malware, right? So when the malware runs, not only does it destroy your computer or record your webcam or ask you for money, but the code will also execute another code segment which sends a copy of itself to everybody else or to other computers. So now it's infecting other computers in addition to your computer. Okay, so we said, it outputs a copy and then sends it to everyone else. So that's self-replicating code. It's kind of a really deep topic of how to write something like this, and we can show you some examples later if you care. Okay. So then now we're talking about viruses and worms. So these are two categories of automatically self-propagating malware. So again, both of these are types of malware where the code will send a copy of itself to other users. A virus is a piece of malware or malcode that requires user action to propagate. So the user has to do something to cause the virus to go other places. So usually what happens here is the computer gets infected, some code gets stored, and then when the user runs that code, the virus gets spread to other users. So the code is stored somewhere, and it's the user's job, or the user has to run the code so that the virus can run and get spread to other people. And then the worm is malware that doesn't require user action to propagate. So with a worm, usually the infection happens, instead of happening on code that's stored and will be run later, it happens on code that's already running, or it injects itself and then executes itself. So that way the code for the worm executes immediately, and the user doesn't even have to do anything. The code is already running, and the worm is going to spread itself to other users. So depending on whether your code requires the user to click on a button or execute some program or open a file, it could be a virus or a worm. So this is kind of a categorization of malware, but there's a lot of malware out there, and some of them could kind of classify as both or neither, or kind of in between. So there's not a clear-cut categorization. You won't say something is for sure. You can't say everything is for sure a virus or a worm. Some malware uses both approaches. So maybe some code runs now and some code runs later when you click on something. Some malware doesn't self-propagate at all, but requires user action to show up. So that's called a Trojan. So if you've ever run antivirus or something, and you see something called like a Trojan horse or something, that's a type of malware that is not going to send to other people, but you have to click on something for it to work. So there are lots of different categorizations. This is just one example. Okay, so how might you get, or why would you want to have something that propagates to a lot of people? Well, one obvious answer is, I want as many people to be hit with the ransomware as possible, or I want to destroy or disrupt as many computers as I can. Right? So as an attacker, you might just want your attack to happen on lots of different people. But one particularly useful reason why you might want to use malware to automatically infect as many people as possible is we can build something called a botnet. And a botnet is a set of compromised machines that are called bots under central control. So these machines, once they've been compromised, they now are under attacker control. So they basically become inanimate bots. They'll just follow instructions. So if the central attacker tells all of the computers on the net to do something, they're all going to faithfully execute that instruction. This gives the owner a huge amount of resources, right? Because they've compromised thousands or millions of computers, and now they can use all of them to execute some instruction, and that gives them just a huge amount of resources. So for example, if you want to perform a denial of service, maybe you compromise a botnet, and that gives you control of a huge amount of computer resources, and then you tell everyone on the botnet to attack one target, and everyone floods the target. So that would give you a ton of computing power. So you can use malware to do this. There are lots of different ways to find a botnet. You can also just purchase one if people are selling them. But one way to do so is to use a virus or a worm to infect lots of different computers. Okay. So I think that's it for botnets. Yeah. Okay, so now let's talk a bit about the two categories of malware that we talked about. So the first one is viruses. Remember, these require user action to propagate. I think that's it for that slide. How would you get viruses to propagate? So let's think about this. Well, first of all, you infect existing code that will eventually be executed by the user. So we talked about that. And some examples, again, are maybe some code runs when you open an app, so some startup code. And if you infect that, then the next time the user opens the app, they'll get infected. Or you can also infect system startup code. So the code that runs when your system boots for the first time, that could also be infected. And if so, as soon as you turn on your computer, the virus executes. You could also have code that runs when the user opens an attachment. So you can email the user some spam and say, hey, download this for free money. And when the user downloads it and opens it, they get infected. Or if the user is looking for movies on some illegal platform, you can say, here's the movie for free. And when they download it and open the movie, it's actually some virus. So those are all ways to do that. Does anyone remember like LimeWire, which is a really old, not legal music sharing website? So LimeWire was very famous for having lots of viruses where if you downloaded the song name, the song file, and you open it, it was just a virus. So you would see things like, I don't know, you would see like Radiohead creep.exe. Like, I don't think music files are .exe, but okay. So you can also modify existing code to include the malcode. So that's kind of some examples from up here. When the malcode runs, now it's going to look for opportunities to infect more systems. So it needs to find out who can I infect next and find another target, and then find a way to send its own code and self-propagate to that next target. So ways I can infect other targets are maybe I'll send the same spam email to other people with the code attached, or I'll copy the code to a USB flash drive. So now the flash drive is infected. And if the flash drive is used to transfer files between computers, anybody else who plugs in that flash drive and runs a file now gets infected too. So you want to find little avenues or opportunities to inject this code in other places and spread. Okay, so how would you detect something like this, or malware in general? One common malware detection is something we saw yesterday, which is signature-based detection. So because things are self-propagating, viruses often use copies of the same code. Right? So we said if code is self-propagating, then the virus is sending a copy of itself to a lot of other people. So as the virus spreads, it is using the same copy of itself on every single computer. So this is a very good target for signature-based detection. Because remember, signature-based detection says, this is a pattern of a known attack. If I see this pattern, I know it's a virus. Well, if I know that this virus has infected a bunch of different computers before, and is using the same code on every single computer, then I can create a signature and say this code snippet or this pattern is a virus. And then all the other computers now know if they see this pattern, they found a virus. So what we can do is we capture a virus on a system. This could be like a honeypot, or maybe an antivirus company will put a vulnerable system out in the wild on purpose. It'll get infected with viruses, right? Maybe that sacrificial computer opens a bunch of malicious files on purpose to look for viruses. And when it sees a virus, now it's infected, that sacrificial computer is done, but it was able to capture the virus and look at the bytes of its code or the pattern of what it's running. And then that lets us create a signature that we can use to detect the same virus as it spreads to other people. So software that does this for you is called antivirus because it's trying to be against viruses or stop them. So you may have installed antivirus on your computer before, and antivirus is just software that is looking for common viruses. And often antivirus uses signature-based detection. So what they do is they have a list of these are a bunch of common viruses that we've seen before. This could be gigantic. These companies could spend and invest money making lists of millions and millions of viruses. And usually what they might do is they'll scan your computer and see if any code on your computer matches a signature. So here we have one called Virus Total. I think this one actually is a bit fancier in that it actually employs multiple different antivirus software. So it uses like Kaspersky is a common one, or like Palo Alto Networks or whatever, right? So it scans all of these, or it scans your computer with all of these different antiviruses, and it sees that a lot of these, have found signatures, or a lot of these antiviruses have signatures that match the virus that's been uploaded. So I think in this particular case, the detection ratio is 11 out of 62. So it sounds to me like for this particular virus, the CC8 CAA blah blah blah.exe, it seems like this virus was detected by 11 antivirus softwares, and not detected by the other 51. Okay, so you do have to have a strong antivirus software, and companies spend a lot of money trying to make good ones. So this takes us to something called an arms race. So in real life, an arms race is kind of when two countries keep piling on more weapons so that they can beat each other. So it's like, oh, that other country made a nuclear weapon, so we'll make one too. The other country has invented a new spy plane, so we'll invent a spy plane too. So they race against each other to see who can build the most weapons. So there's kind of a same race in antiviruses versus attackers. So viruses have been around forever, and there's a race between attackers who try to write new viruses. Then the companies look at the new viruses and try to detect them. Then the attackers try to find ways to avoid the detection. So they go back and forth and back and forth. And as this race continues, the malware evolves. So this race of attackers trying to find ways to avoid the detection and the detectors trying to find ways to capture the attackers, this has influenced like modern strategies for how malware propagates. And we'll see some of those. So in general, attackers are looking for ways to avoid detection. So they're looking for evasion. So they want to change the appearance of the virus or somehow make signature-based detection harder. Okay. So again, we want viruses and worms in particular to spread automatically. Right? We want self-propagating code. We don't want to have to manually infect a lot of different computers. So we still want a way to automate this process of evasion, and that's something we'll see, I think, on the next slide. So we want to change the appearance to avoid detection, and we want to do so automatically so that no one has to manually go through and write like 5,000 different versions of a virus. So in this race, there's not a clear winner because both sides are kind of going back and forth. But if you had to ask who had the advantage, it would probably actually be the attackers. And the reason there is because it's kind of like attackers move second. So the attackers can see what the antivirus is doing and then write evasion strategies to go around the antivirus. So it's kind of like the attacker knows the system. Right? So that gives the attackers a little bit of an advantage because the antivirus goes first and says, here's my defense. And then the attacker goes around that. But on the other hand, the attacker is not going to tell the defending companies, here's my virus, try to write some signatures, right? So they're not going to do that. So usually because the detectors have to publish their code first, they are at a bit of a disadvantage. Okay. And again, the antivirus companies can't see what the attacker is planning. So that gives the attacker a little bit of an advantage. Okay, so how do we write this code that automatically changes itself and still spreads automatically? So one way to do so is something called polymorphic code. And basically what happens here is every time we spread the virus or propagate it, we're actually not going to spread a copy of the virus exactly. We're going to insert an encrypted copy of the virus code. And the code will also have the key and the decryptor so you can decrypt the virus back into its original form. So be careful here because I guess first we'll talk about why this works. So the reason this works is because if you remember for crypto, the encryption scheme produces different looking output every single time, right? So if you're using some NCPA secure encryption scheme, when you encrypt something 10 different times, the output looks different and random and totally unpredictable. So if I use a different IV or if I use a different key, then I get different looking output on the repeated encryption. But be careful here because we're not using encryption to hide the contents of the virus. So we're not here to make it so that other people can read the virus, right? The point is to execute this virus code eventually, so we will be decrypting it. So the goal here is not confidentiality. We're not trying to make it so that people can't read the virus. We're actually using this for something different called obfuscation, which is just a very fancy word for making things look different. And what we're doing here is we're trying to make every copy of the virus look different. And that will allow us to avoid detection. Because if all the copies look different at random, it's very hard for a signature-based detection to look at the bytes and say, oh, this is the shellcode that's being used. But the goal here is not confidentiality. So in the end, everyone is still able to open the virus contents, right? Our goal, or the attacker's goal, is to make everybody open the virus and execute the virus. So at the end of the day, everyone is still going to be able to open the virus and read it. And in fact, if you remember, the code that we're sending is not just the encrypted code, but we're literally sending the key in plain text and the decryption code in plain text. So the code itself includes the tools to decrypt. So it's not confidential in that we don't want, it's not like we're trying to make other people unable to read the code. We're trying to make it so that the code looks different every time. And it just so happens that encryption is a useful tool for that. But again, everyone will eventually decrypt and execute the virus, or at least that's what the attacker hopes. Okay, so this also means that we don't have to use something perfect. It can just be any old encryption scheme. It can even be something like, I guess, ECP mode if you felt like it, but anything is okay as long as you use plain text, or as long as you make sure it looks different every time. And this also means you can store the key in plain text because you don't care about confidentiality. All we care about is making the virus look different. Okay, so here's an example of polymorphic code. So the original virus is just one block of main virus code. This stuff in red is, I guess, the virus code. And notice that if you copy this from machine to machine, it looks the same on every machine, right? Just this red block of code. So for a signature-based antivirus detector, it's extremely easy to look at this code and say, oh, this code matches a signature from previous detected viruses. So this must be a virus. That's very easy. But look at this polymorphic virus. This is a little bit harder because this virus has an encrypted blob of virus code. So this blue blob looks different every single time because it's encrypted differently every single time. Here's the key. It's in plain text because we don't care who decrypts this. In fact, the attacker wants everybody to decrypt this and execute it. So this is okay to have the key in plain text. And in fact, we're also going to give you the code for decrypting. So what happens here is if this code were to be executed, this decryptor code would execute first. This is in plain text. So we don't encrypt the decryptor. So we execute this. This uses the key to decrypt the virus code and now execute the virus code. Okay, so the decryptor code says, again, use the key to decrypt the encrypted virus and then execute it. Now, someone asked a really good question, which is, can you still detect the decryptor code? That's a very good question. And I think like 2 slides from now, there's an answer. But that's definitely kind of the antivirus company's way of thinking is, well, this code still looks the same, so can I decrypt this? But that's a very good thought. But before we get to that, here's an example of how you might encrypt the code differently. So you can use different IVs, for example, but one strategy that doesn't really work in encryption, but works very well here, is to use different keys. So because the keys are in public and we don't care about their security, and we also just don't care how many keys there are, we can actually use a different key to encrypt every single virus. So what happens here is, here's one copy, here's one copy. These 2 copies have the exact same decryptor code, but because they use different keys, the encrypted virus looks different. So this blue on the screen looks completely different. And what happens here is maybe every time you spread the virus, you change the key and then encrypt it with a different key so that the next person will still decrypt it correctly because they have the new key, but because it's a different key, the encrypted code looks different. And down here, there's the encrypted propagation code. So once the decryptor code decrypts the virus, it'll also execute, in addition to the virus, this propagation code, which says, encrypt the virus again and spread it to someone else. So you use a different key or use a different IV or use something different to encrypt the virus and send it to someone else. So now, instead of having this gigantic red blob to detect, the antivirus is down to just the decryptor code. And we'll see why this might be trouble. This might spell trouble for detectors. Okay. So again, these 2 copies use different keys, so everything looks different. And again, the only thing that looks the same here is the short piece of decryptor code. Okay. So as someone just said, the one strategy for this is to add a signature for detecting decryptor code. So the decryptor code probably looks the same in every single virus. So why don't we just detect the decryptor code? Well, one issue here is that there's less code to match against. So signatures are very, very powerful if there's a long piece of code. If the virus is very long and looks identical every time, then it'll give you very low false positives and very low false negatives if you detect on every single piece of that long piece of code. The problem with decryptor codes is that they're shorter, so there might be more false positives. This short piece of code could actually appear in legitimate code as well. Because if you think about it, all this code is doing is saying, use this key to decrypt this code. That's a pretty common pattern that a lot of different legitimate pieces of code will use, right? You can imagine a legitimate piece of code like your project 2 will also say, use this key to decrypt this code. Or, I don't know, some email service could also say, use this key to encrypt this email or decrypt this email. So decryption code is kind of common in legitimate applications too. So now you could be running into false positives where some code gets flagged as a virus just because it's saying that something should be decrypted, even though it's not really decrypting the virus. Another kind of strategy to avoid detection is to scatter the decryption code across different parts of memory. So instead of putting it in one chunk at the beginning, maybe you take some existing code and you put one instruction at the front and then say jump here, and then the next instruction is somewhere in the middle, and then say jump here, and the next instruction is here. So if you jump around, instead of having one chunk of code to match, you're actually, the decryptor code is actually lots of different instructions scattered across some existing code. That would make it even harder to find because now you have to match all these small instructions, which could be very, very hard. So that could also be a way to avoid detection. Another strategy is just to run the code and see if it decrypts stuff. So if the code decrypts stuff, then it could be a polymorphic virus. So what you can do is you can open a sandbox. And remember, a sandbox is an isolated environment where if we run something and it goes horribly wrong, it's okay because it doesn't break anything outside of the sandbox. So like a virtual machine would be a sandbox because if you destroy the virtual machine, the computer outside is still fine. So if we perform an isolated test of this code and run it, that lets us analyze what the code is doing without really executing the code, or I guess without executing it in a dangerous environment. Another way to check is to analyze the code structure without executing it. So maybe just look at the code and see, are these instructions for decryption? If so, maybe this is a polymorphic virus. Or analyze the code and see, wait a minute, the decryption key is in plain text. That could be a sign that we're in polymorphic. We have the polymorphic virus. And again, the issue here is that legitimate programs will probably do the same thing, right? So one example of, I think zip files sometimes use encryption and decryption algorithms, I suppose. So that could also be a case where the decryption algorithm is confused with a legitimate program that's using a decryptor algorithm. Okay. And then there's also the problem of how long you let the code execute before you're sure that it's a virus. So if you're trying to execute the code in a VM, the attacker could do something very clever, like the code could say sleep for 1 day, do nothing for 1 day, and then a day later execute the virus. So if you only let the code execute for 10 seconds or an hour, then you're not going to see anything because the code is still sleeping for a whole day. And the antivirus will say, I tried this code out and nothing happened, so it's probably safe. But in fact, the code is not safe because a day after you open it up, it is going to execute and run a virus. So that's something dangerous to keep track of. So that's one way to make code look different. Another way is called metamorphic code. So metamorphic code says, every time you propagate or spread the virus, generate a different version of the code, a semantically different version. So you can do things like reorder operations or change variable names. And this means that the code itself is still doing the same thing. It's still infecting your computer or deleting files, but the execution itself is going to be slightly different every time. So reorder instructions or change variable names, or instead of a while loop, use a for loop this time. Do some minor changes that makes the code look a little bit different every time. And to do so, you want to do this automatically. So you probably have to have a code rewriter or a compiler to change the code randomly every single time. And modern high-tech hacking equipment usually does have something like a code rewriter for this. So one thing you can do, if you remember x86 or RISC-V, those use registers and they store information in registers. So you can renumber the registers. Instead of storing my temporary variable in T0 or X0, I'm going to store it in X1 or T1. So I can change where the virus is storing information. I can change if-else statements. So instead of having the if case run first, I'll let the else case run first. Right? I could reorder operations. I could change algorithms. So instead of using merge sort, I'm going to use quicksort this time. These will all cause the code to look a little bit different. So if the detector is very basic and just doing kind of a string matching or a byte matching to see, does this match the entire value from before? Well, now that I've changed the code, it no longer matches exactly. So this is kind of like when I don't recommend doing this, but if you're copying homework from your friend and your friend says, yeah, you can copy that homework, but change it up a little bit. This is what metamorphic code is doing. So it's copying homework, but it's changing it up a little bit. So they change the sentence order or whatever to make sure that the teachers don't notice cheating. But don't do that, kids. Do your homework. And you can also add dummy code. So add some random for loop that does nothing, or add some unused variables, and those will also get compiled maybe and cause the code to look different. Okay, so here's the polymorphic virus. It's kind of the same as before. We have the virus code and the rewriter, and then the code itself executes. Then the rewriter executes and says, construct a new version of the code that does the same thing but uses some different variables, and then spread the new version. And one thing to notice here is that, in fact, you can also modify the rewriter code. So this rewriter code is also just a code snippet. So maybe you can also change the order of operations or some algorithm inside the rewriter code so that the entire virus looks different every time. So this one is in a blue and is orange, and this one is green and purple. So it's different every single time. Someone said, is that supposed to be metamorphic on top of blobs? Oh, yes, you're right. This should say metamorphic. So that should not say polymorphic. Good catch. Okay. So how do we stop this? Well, because code is changing now, instead of using signature-based, right? This is not good for signature-based because these two look completely different. So there's no real easy pattern to find the virus anymore. But this gives us another really good detection system, or this lets us use another really good detection system, which is behavioral. So now, instead of looking at what the code is, let's take a look at what the code does. So let's stop looking at syntax because we know the syntax is changing. Let's look at the behavior of the code. So what is the instruction doing? Is it opening a file? Is it, like if this virus is always targeting someone's passwords file, maybe that's a good sign that it's a metamorphic virus. And so what the companies will do is they'll analyze the virus, see what it's doing every single time, and figure out what's a common behavioral signature. So maybe it always does one thing, like it always finds a passwords file or looks in a certain location for a passwords file. And that lets the software, or that lets the code kind of have a signature that the antivirus company can use to detect future copies, even if they look different. But of course, remember, it's an arms race. So once the antivirus companies start using behavioral detection, the attackers are going to subvert that and do something different. So again, they'll try the delay strategy where they wait a long time before executing. So if the company only runs the code for an hour, they'll be like, well, nothing happened with this code, so I don't even think it's a virus. But it turns out a day later, the code does execute. You could also be really clever and say, if the code's being analyzed, so we realize that the code is being run in a debug environment or a virtual machine, then do something different, make it look legit, and that'll also stop the antivirus or make their lives harder. And again, it's an arms race, so guess what? Antivirus companies will understand that attackers are doing this stuff and try to subvert them as well. So maybe the antivirus learns that attackers are delaying things, so the antivirus will say, okay, actually, I'm going to execute your code for a day, or I'm going to skip any statement that says sleep, or I'm going to artificially make time go faster so I can detect things. So again, it's an arms race. Every time the attacker figures out something, the antivirus will figure out a defense. One good defense here is to flag unfamiliar code. So it turns out, theoretically, there's no such algorithm that says this code is malicious and this code is safe. So that's too perfect to exist. And in fact, if something like that exists, I believe you will be able to solve the halting problem, which is proven to be undecidable. So if you remember from CS70, there's a halting problem. This is kind of like the halting problem. It's an impossible problem to solve. And that's how it goes. So if you don't know what the halting problem is, no worries. But instead of trying to write an algorithm to see what's malicious and what's not, the antivirus software could do something a little bit different. And this is kind of like specification or anomaly-based detection. And instead, now they look for new unfamiliar code. So if it looks different, flag it. So they keep a central repository of common previously seen code. So they're like, oh, this code comes from Google. They published it, so it's probably okay. This code I found on GitHub. that was published by some other company, so it's okay. So they keep some central repository of code that's seen before. And if some brand new code comes over, then that's something that should be treated as suspicious. So if the user is installing a program that the antivirus has never ever seen before, that could be a sign that it's a virus because it's never seen this code before. If you want to be a little bit efficient, you can store hashes, but I don't think that's too important. So flagging unfamiliar code is great because now you have two pieces of detection that work together. So you have a detector for malicious behavior, so that's the signature-based detection. Then you have a unfamiliar code flagging defense, which is kind of like specification-based or whitelisting. And that will catch people avoiding your first detector. So basically, you kind of have the whitelist and the blacklist working together. So you have a whitelist for what's allowed, and you have a blacklist for what's not allowed. And if you put these two things together, you're going to make the attacker's job very, very hard. Because basically what happens now is the attacker is screwed either way. If the attacker wants to keep the code the same, that's a signature. So the signature-based detection will catch that. What if the attacker says, instead, let's try to modify the code? Well, if you modify the code, it's going to look new every single time, and that'll be suspicious, and it'll be flagged because the whitelist has never seen this code before. So this is a very, very powerful double defense. So you keep the blacklist and the whitelist. So now the attacker has to pick one of these two. If they choose to keep the code the same, they're out of luck. If they choose to modify the code, they're also out of luck. So this is a really, really good two-part defense in depth. Okay. So again, if you avoid one strategy, you're going to get caught by the other strategy. So it's very, very hard for the attacker now. But of course, they'll still find ways to subvert this because it is an arms race. Okay. Here's one kind of just side business note. So if you're going into advertising, one good thing you can do is take advantage of polymorphism and advertise how many viruses you have. So remember, in polymorphic and metamorphic viruses, there's different variation per computer. So you can actually classify one type of virus or one piece of virus as thousands of different viruses because it looks different every single time. Now, if you are an advertising executive, so if you quit computer science and move into advertising, you might see this as a very good business opportunity. You see, well, wait a minute, you're telling me that this virus looks different on every single computer, which means I can plausibly say that instead of one virus, there are 5,000 viruses that I can catch. That's a pretty good advertising statement. So this is something that some advertising companies do, so be wary of this. So maybe the company will create a signature for every single variant and advertise, say, I can detect 10,000 viruses. That's so powerful. Even though probably what they should have done is have a fewer number of signatures that are stronger. So this is something that antivirus companies can do to make their product look good. So here's an example of that. Like, look at these numbers. This says in 2021, there are 1,200,000,000 viruses. Now, and it says what? How many viruses are there per day? 350,000. Whoa, that's a lot of viruses. Now, do we really think that attackers are writing 350,000 programs per day? I mean, maybe it's possible, not impossible. It's like not out of reach, but it's a little bit unlikely to me that they're writing 350,000 per day. So maybe what this institute is doing is they're counting variants separately. And so what they've done here is like, if the virus is polymorphic and is spread to 10,000 different machines, it looked different 10,000 times. So this company decided to count it as 10,000 different viruses. And now, attackers or consumers are thinking, wow, this must be great software. It can catch 350,000 new pieces of malware per day. And it's caught 1 billion pieces of malware this year. Oh, this must be a really strong company, even though they might just be doing, something kind of sneaky. So do be a little bit careful, right? Like, in addition to being a good computer programmer, you also have to be a good consumer and know when to use a good software when softwares are being a little bit sneaky with advertising. Okay, so yeah, these people are probably overcounting. Okay, I think we've gotten to worms and we're almost done. So I guess let's take a quick 5-minute break and come back at 4:40. Sure. Okay, welcome back. If you were not here, we watched a movie and then we came back. I'll show it to you at the end, so stick around. Okay, but first, let's talk about worms before we do anything fun. So first, we have to talk about worms, which are pieces of code that don't require human action to propagate. So as we said before, we usually infect some already running code. So the code's already running, the worm injects itself, the worm executes, and then the worm spreads to other people. So this is unlike a virus. That should not say malware, that should say virus. Unlike a virus, no user interaction is required for the worm to spread. So how would a worm spread? So this is a little bit different, I guess. How does the worm find new users? Now, the strategies from the virus are not quite relevant here. So remember, the virus had strategies like send an email to someone so when they click on it, the virus executes, or put it on a flash drive so that when other people run the flash drive, the virus executes. But those are for stored pieces of code that are executing later. So that doesn't work for worms. Worms want to execute right now, right here. So for worms, some other ways to infect are they usually have to inject the code directly. And to do so, first they have to find a lot of different machines. So to do so, they can randomly choose a machine by generating a random IP address and connecting to it. And if it fails, just try another one. And eventually they'll probably find a lot of IP addresses. They can use search worms, so they can use Google searches to find a lot of different servers to infect. So search for some random company and you'll probably get a lot of results for that company that you can infect. Or go on social media, you'll see lots of different users to infect. You can look for targets by doing some smarter scanning, but this can take some bandwidth, so maybe you're limited. You can also get a list of targets. So maybe you can buy a hit list from some illegal place. That's a pre-generated list of targets that you can hit. You can look on the host. Maybe the host has like an email list or a contacts list. That could also give you a list of people to infect. You can also ask a third-party server, like a DNS server. That'll tell you lots of different servers that you can infect. So these are all ways you can find a new user to infect. And unlike a virus where you just send an email and hope that they click on it, with a worm, you're going to directly inject the code to this person. So to do so, you have to find lots of computers very, very quickly. And these are all ways you can find different computers. You can try randomly, you can use some searches or go on Facebook or Twitter to look for victims. You can also be kind of passive. This is a little bit slower, but you can wait for other people to contact you and then reply with the infection. And then how does the worm force code to run? Now, remember, you have to infect existing code. So you can do something like buffer overflows that injects into existing code, or you can use XSS that injects into almost existing code if the users, or if you force the user to click on the link, and that'll happen right away. So those are all ways you can force code to run, and these are the ways you would find people to propagate to. Okay, so how do you model worm propagation? So now that we know how things propagate, let's get an idea of how fast worms can propagate. So if you think about it, the process parallelizes eventually. So you basically get exponential growth. So if you think about exponential growth, the more computers are infected, the more computers are spreading the worm, because every single computer is trying to spread the worm as fast as possible to as many people as possible. So you basically get exponential growth. And so here's your first computer. It spreads to 2 people. Both of these computers spread to 2 other people. And then all 4 of these computers spread to 2 other people. So you're getting exponential growth. Now, this is also kind of true for viruses, but it's not as fast because remember, viruses have to wait for the user to open the file. So if the user doesn't open the file till later, then that's a lot of wasted time. But in worms, we're trying to execute immediately. So this exponential thing can explode really, really fast. And in fact, this is kind of similar to something else in the real world that we've modeled before. And these are infectious epidemics. This slide has been around for many years, but it's a little bit more relevant today because there is one of these going around. So these are the same models that people use to model pandemics or infectious diseases. These can actually be used on worm propagation as well. And the reason why is because the factors that tell us how fast a worm spreads are very similar to the factors that tell us how fast a disease spreads. So if you think about it, the spread of the worm depends on what's the size of the population, how many computers or how many humans are vulnerable to being infected, or are there, how many humans are there in the population? Also, how many of the humans or how many of the computers are vulnerable to infection? So maybe in the disease, like with a coronavirus, it's like older people are more vulnerable to infection. And maybe in a virus or a worm, it's like only computers running Windows are vulnerable, or only computers running this software are vulnerable. So we have to see how much of the population is actually vulnerable to being infected by this worm. And then it also depends on how many hosts so far have been infected. Like we said, the more hosts have been infected, the more hosts are spreading this worm. So the faster things can go up to a limit. And then there's a contact rate. So how often is this host communicating with other hosts? So if one infected host can spread to 10 other people, that's going to be really fast. But if one infected host can only spread to 2 people, that's going to be slower. So this is kind of how, like, if you have a lockdown or if you're doing social distancing, the contact rate goes down. because you're communicating with fewer people, and that's going to slow the rate. So similarly, if you have an infected computer and it's communicating with fewer people, then the worm is going to spread slower. So these are all things that happen in real life, and biologists and epidemiologists have modeled it. So computer scientists have just kind of stolen that model and run with it, and it turns out to work pretty well. So here's an example of a worm in the real world that spreads, and here's a model that we used. And the reason why they're so close is because, again, we're borrowing from the real world and using an epidemic model. And basically what you get is not quite exponential forever because there aren't infinitely many hosts to infect. What you get is actually what's called logistic growth. And logistic growth says you start exponential, so this initial ramp up is really, really fast. But toward the end, it's actually going to taper off and become flat again. And the reason why is because, well, we start exponential. So again, we have, one person infects two people infect 4, 8, 16, so it doubles every time. That's exponential. And that's because the more infected hosts there are, the more people you can infect. But if you've gotten to the point where almost everybody is infected, the growth is going to slow because almost everyone is infected. There are fewer people to even find for infection. So later, as the virus ramps all the way up, or the worm ramps all the way up to the maximum, and you've almost gotten everybody infected, the growth will actually slow because there are fewer non-infected hosts to infect. So we obviously didn't get this far with the coronavirus, thankfully, but you might remember a couple, politicians or whatever were saying things like, let's just infect everybody and then it'll never spread again, which is kind of true in this case, right? If you have the worm infected everybody, then the worm is going to stop spreading because there's nobody left to infect. Of course, you do not want the worm to get this far and infect everybody, but if the worm is fast enough, it can definitely get to this point. And this is a very good model because, as you can see here, right, the number of scans, which is in blue, that's the actual growth. And then the red is a logistic growth curve. So they're very, very close for a real world worm, which is called code red. So you can see it's very good for modeling the spread of worms. Okay, I think that's it for actual topics about worms. So the rest of this is just for fun, take a look at the history of worms. So the very first worm was called the Morris worm. This came in 1988. This is usually considered the very first one. It's very influential. I think a student at MIT wrote it just for fun and then accidentally sent it out and it just immediately blew up the whole internet, which is kind of crazy, right? So what did it do? It exploited buffer overflows, guessed some common passwords to log into people. It activated a debug configuration to give it shell access. It exploited user accounts. It found people by looking inside the local subnet, so the local area network, to find other people. It looked at the network configuration to see if there are other machines. It looked at the user files to see if they mention other hosts. So we've seen all of these before. And yeah, this one was pretty bad. I think the student who accidentally, maybe not even accidentally, but they claimed that it was accident. The student who accidentally infected everyone with this worm, I think they ended up either going to jail or paying a lot of money. So this just shows you, do not write malware for fun. That is probably not a good idea. Okay. Then came Code Red. This is usually the first modern worm, or at least that's how people consider it. This is the one that we saw before with that logistic curve. This came in 2001. And basically what they did is they put messages on vulnerable websites, and they also did a DOS attack against the White House website. So what they did is every single month you spend 20 days spreading. So for 20 days, your job, the worm's job, was just to spread everywhere. And then for the other 10 days or 11 days, you flood the White House and DOS the White House. So the White House's website is no longer accessible. This got so bad that the White House actually had to change its IP address to temporarily stop the DOS attack. And how did it infect people? It exploited a buffer overflow, so we see that a lot. And yeah, I guess one thing that to note here is that there was a fix for this vulnerability that they used, but the fix was announced 1 month earlier. So a lot of people did not patch their systems, and what happens if you don't patch is you're now vulnerable to this worm. So even though the fix came out earlier, because very few people adopted it, this worm was still very dangerous. As you can see, they still use random scanning to find people. Right? The problem with random scanning is if they're using a PRNG for randomness, initially every instance used the same seed. So guess what that means? That means everybody is trying to infect the same computers because everyone has the same PRNG seed. So every copy of the worm is trying to infect the same computer. So you get basically a linear spread. You get one new worm per minute or something. But then they revised it 6 days later to use different PRNG, and now we got that logistic curve that you saw earlier. So this actually was a buggy worm at the beginning that fixed it and it became logistic. Here's one called Slammer. This one went really fast, and it went so fast because it used UDP instead of TCP. So remember, UDP is fast, doesn't need a three-way handshake, so that's really fast. Even better, the worm is so compact that it fits in a single packet. So basically, this created something called fire and forget. You send off the UDP packet to infect, and then forget about it. If it works, great. If it doesn't work, just send more UDP packets. So a single computer can flood UDP packets and infect thousands of other computers with just a single infected host. So this was ridiculously fast. And we're talking like in 10 minutes, they hit 75,000 computers. But we're talking like every 10 seconds, the number of hosts doubled. So this is just ridiculous, mind-bendingly fast. This got so fast that it stopped the logistic curve. So remember, logistic curve says you go up till the capacity, which is above this, and then it flattens out. But in this case, before it got to the capacity, it already started flattening out. So it's stopping logistic. And the reason why it's stopping logistic is because Slammer was so fast that the internet itself could not handle Slammer. The internet itself was completely clogged up because every single node in the internet was too busy sending Slammer already. So no more packets could be sent. And that's why the exponential slowed down before it hit every computer. So this Slammer worm was so bad that it basically broke the internet for a day or for however many minutes. I think it took like 12 hours or something before it got fixed. So basically for 12 hours, the internet was not usable because every single packet going through the internet was just Slammer worms. And that's how bad it got. So well, yeah, worms are very dangerous. It's one way to bring down the entire internet in the world. Another one called Witty kind of did the same thing, so just go really fast. This one took a while to fix. Again, the patch was there 36 hours before. People already knew this was a problem, but because people take time to patch their systems, this worm was still dangerous. And apparently this one just deleted file systems. So if you got hit with Witty, then your file systems were gone. Okay, let's talk about this one. This one's fun. It's called Stuxnet. So this one came in 2010. This is a very weird worm. So one weird part of this worm is it used something called 0 days. So if you remember, a 0 day is a vulnerability that no one knows. So you are going to be the very first person to use it. There are no defenses yet because nobody knows about it. So when you use it, it's guaranteed that it's going to work because there are no defenses yet. These, as you can imagine, are extremely expensive. To buy or to discover a 0 day is very valuable because you have a vulnerability that nobody else can fix yet. So you are guaranteed that it's going to work. Now, 1 0 day is expensive. Stuxnet used 4 0 days. So we're talking like astronomical millions of dollars to create Stuxnet. Right? This is just maybe the most expensive worm ever created because of how many 0 days it used. And then it did some things that are even more kind of unprecedented. So it stole private keys from certificate authorities. As we saw, this requires either giving the certificate authority a lot of money or carrying out a very sophisticated attack to stop or to compromise a security authority, a certificate authority. And this let them sign code that's trusted by the victim because certificate authorities sign some code. And again, they used USB flash drives as we've seen before, and they use something called Windows remote procedure calls. Those aren't too important. Let's talk about the payload because for a worm that's this ridiculously expensive, the payload was kind of weird. So this payload, it actually didn't do anything to most computers. So if your computer has Stuxnet, actually nothing will happen. The only people who were affected by Stuxnet were people who had computers that were connected to centrifuges, which are these large rotating scientific devices operating at this specific frequency, which is also the frequency used for nuclear weapons. And what it would do is it would increase the speed of the centrifuge, causing the centrifuge to just physically stop working or fly apart. And then it would also send fake readings from the control system to indicate that nothing was wrong. So this is a very specific payload. And once it's over, the frequency will go back, even though the entire thing is already broken. And so the employees will not know anything went wrong. I guess I just spoiled it with my sticky fingers. But as you can imagine, this was not something created by hackers for fun or some, I guess, for fun hacker or for money hacker. This was actually created by governments. So later, people noticed that because of the unprecedented cost, it was so expensive, and because it was targeting such a specific thing, it was probably created by the United States and Israel. So these two governments actually collaborated and made a cyber weapon called Stuxnet, and its only goal was to target Iran's nuclear program. So yeah, as you saw in the first lecture, we said security can affect the operation of entire governments and politics, and this is one example of that. So this is a modern cyber weapon. There are some other ones. Here's one called WannaCry, which infected computers and put ransomware on there. So remember, pay Bitcoin or else the data is gone. The problem is this one actually had bugs, so it didn't work. So if you got infected with WannaCry, it was buggy, so you could probably just get your data back. That is a little bit funny. So worms just don't work. And I think the United States has accused North Korea of being responsible for this one, but I don't think it's been confirmed. So believe what you want to believe on this one. There are more. This one is another cyber weapon, so I won't spend too much time on it, but this one was from Russia to Ukraine. And again, it was trying to hit some tax software. Apparently, I didn't even finish the slide, but yeah. So basically, this one wiped machines on tax data and affected the economy of Ukraine. Okay. And some companies even went down because of Petya. Okay, really quickly, how do you clean up? I realize I only have a minute left for this, but fortunately, the solution for cleaning up is very short and very easy. So you can try restoring your files, and you can try using antivirus to help disinfect your computer. But what if the malware used admin privileges? Now they're hitting the entire computer. They could even hit the operating system. You could try to rebuild the operating system, right? But what if the malware infected those tools to rebuild the operating system, right? So basically, what we're saying is the best way to clean up infections is, well, there isn't a best way, right? No matter what you do, something can be infected. And this is related to a talk from 1984 or 1983 given by Ken Thompson. I think it was a Turing Award winning lecture or something like that. So this is a very influential lecture, and it basically talks about what we just talked about here, which is if I have some code, it's compiled to an executable, and someone hits the executable to be malicious, you probably want to recompile. So let's recompile. What if they hit the compiler? Now the compiler is broken. So we have to recompile the compiler. But what happens if the compiler is broken for the compiler? Now the compiler itself is also broken. So basically, it's very hard to find something to trust if you know that an attacker is present. Right? So it's very, very hard to trust, basically. Even if you have malware on your computer, you can like, oh, let me just delete my files. But what if it's in the operating system? Let me rebuild my operating system. What if it hits my operating system? My code's rebuilt the operating system. So it's very, very hard to find malware and clean it up. And this is something called a rootkit, which is malcode that hides its presence inside the operating system. And those are called rootkits because they're running as like the root user. Right? There's some information about rootkits, it's optional, so we'll skip it for now. But they're very hard to find. And basically, the best recovery solution here, and I think this should probably be a regular slide, is delete everything and start over. So just drop the nuke, take your computer, throw it in the trash, and start over. Because again, even if you think you found the malware, it could be hiding deeper inside the operating system. So the number one solution to fix malware if your computer is infected is to have a good backup, delete everything, and start over. And that's the best way to defend against malware. So this section, basically just remember, if you have malware, just nuke and start over. Okay, now we're at the summary. So we talked about malware today. Malware is attacker code running on victim computer. It can do a lot of different things. It can stop nuclear programs. It can shut down companies. It can ask you for ransom. It can run a buffer overflow, do some software attacks, delete your files, a lot of different things. It usually uses self-replicating code to spread automatically, so it can spread far and wide. Viruses require users to click on something or open a file to spread. Worms do not require that. The ways to detect this are to use signature-based detection, or to use antivirus, or to flag unfamiliar code. So have a whitelist and look for anything weird. The ways to propagate are to encrypt the malware with a different key, so that's polymorphic code, or to change the semantics, which is metamorphic code. This helps us get around signature-based detection. And it's not on this slide, but remember that worms follow logistic growth. So it starts exponential, but will slow down as everybody in the world has been infected. And remember, the recovery method is just to reset everything and start from scratch. And the reason why that's the recovery method is because you have these things called rootkits, which are malware that dig so deep into the operating system or the building of the operating system that it's just impossible to get them out, even if you try to rebuild stuff. So your best bet is to delete everything and start from scratch. So that's malware. We're done a little bit late, so sorry about that. But if there are no last questions, then we'll see you tomorrow for the final in-scope lecture. Okay, there's no questions. Before I stop the recording, I do have something I showed people on break that I can show you now, which is something called, or not something called, but it's or I guess since we're short on time, maybe I won't show it, but if you're interested, I'll just tell you where to look for it because Zoom video sharing is pretty terrible. So if you're interested, what you do is you go to the slide deck and you go under Stuxnet, and it's not as surprising because I've already shown it to you. I showed it to the students beforehand, but there was a movie in 2015 that actually depicted Stuxnet. So the director or the writer knew about Stuxnet and they actually filmed or created like a CGI copy of it. So if you're interested, the link is here, and it basically shows you what we talked about here, which is that someone sends a virus and it enters a nuclear, I think for the movie, it's like a nuclear reactor. And what they did was they basically stopped the centrifuges, but they also glitched out the readings to cause the readings to look normal. So if you watch this scene carefully, you'll actually see that they imitated Stuxnet pretty accurately, which is kind of surprising. So for your entertainment, if you want to watch something, you can do that. Although I don't think the movie was very well received, so watch the whole movie at your own risk, but the first scene is actually just Stuxnet, so that's cool. Okay, so that's all I have. And if no one else has anything else, then we'll see you all tomorrow.